Hello, everyone, and welcome to a new episode of AMA with Dan Hughes. My name is PiersDole. I am the CEO of RDXWorks, a core developer of the decentralized finance protocol Radix, a public ledger entirely focused on bringing DeFi into the mainstream. Today, we are going to be going through some AMAs that have been hanging around and some that are new ones to get the questions from the community answered by Mr. Dan himself. This is going to be our last AMA for a while. It's actually going to be about a month until our next one because both of us are going to be traveling and doing some work, including things like consensus and the foo hack and a bunch of other stuff. So this will be the last episode for a while, so we'll make sure that the answers are nice and snappy, and we'll jump straight into it. So first question by surf.xrd. On Telegram. Who stores the transactions? From what I've gathered, the entire transaction history is not held by every node and is discarded every epoch or couple of epochs. This is not good in any way, shape, or form, since it inherently means new actors in the system have to trust the old actors who have not cheated, right? And then the second part of this question is a PostgreSQL database used for this? Mr. Dan.
Okay, I'll do the second one first because that's nice and snappy. I believe it is. It did change, but I think it changed to a PostgreSQL database. Maybe Russ can correct me on that, but I believe it does. And the first one, a bit more complicated answer, not quite as snappy, unfortunately, appears, but I'll try and keep it short as possible. So transactions don't get pruned every epoch. I think what's happening in this question is it's more of a question around maybe some confusion to do with sharding, right? When you've got validator sets of replicas, and you want to move replicas around periodically so that if you do have a bunch of malicious replicas that have managed to find themselves in a set, you don't want them to stay there forever because more replicas might find their way in that are also malicious, and then you end up having an issue. So what actually happens in the case of a validator is moving from one particular set to another one, then obviously the state that they currently have stored, if they're moving to another validator set, most, if not all, of the state that they're currently storing is redundant. There may be some shared transactions between the two sets, maybe, but other than that, most of the stuff that they have is useless to store. So what these validators will do as they move, they will prune all of the stuff that's no longer their responsibility, so get rid of it out of their database to free up space. And when they join the new validator set, they will synchronize with the new validators. They'll say, okay, I've come from here. This is what I've got that's common between those two validator sets, where I've come from and where I've moved to. Can you guys give me the rest of the stuff that I'm going to need so that I can perform validation, verification on state transitions, right? So then they will synchronize with that new validator set. So you never actually prune anything for entirety, right? Because I'm pruning what I don't need and moving to somewhere and getting a copy of the stuff that I need. But then anybody that's moving out of the validator set where I've just moved to, they'll be doing the same thing, right? So your validator set always stores transaction history that's relevant to that validator set, which will be serving X number of shards within that group, right? Now, obviously, there are a few additional questions that you can raise here, which is like, well, over time, right, the amount of data that's going to have to be synchronized when a validator moves is going to increase, yeah? So, let's say that the demand on the network is, say, 1 million TPS, right? And it just plateaus at that and it stays there forever. Doesn't increase, doesn't decrease, right? And then you've got, say, I don't know, so you've got 1,000 validator sets, right? Then each validator set is going to be processing, let's say, 1,000 transactions a second in this particular example. And that's just going to grow perpetually over time, right? Because you want to keep all of those transactions, and new validators that come in, they will be synchronizing up with that ever-growing 1/1000th of what the current transaction stuff is. So even though not actually pruning anything in terms of moving, under those kind of conditions, you would actually want to say, well, actually, what can we prune out here, right? What can we maybe just get rid of? It's no longer needed, or is there a way that we can take that state, the kind of historic state, and turn it into a more compact representation, which you can do as well, and all these other bits and pieces, to reduce that synchronization time of a new validator coming into that set. There's also some tricks that I've been looking at where I can synchronize in reverse. So I can get the current live set of state, get that first, and then synchronize all the history. So even though I've still got maybe quite a lot of synchronization to do, I can at least shortcut around that synchronization and say, okay, just give me the latest stuff. I can take part in consensus with most things that happen. And maybe only a minority of stuff where I need some historic state that I don't have yet. I'm going to have to abstain from taking part in consensus in those kind of situations. So there are a lot of things that you can do to reduce that load. And then obviously, as many people know, the kind of really long-term forward-looking is like all the statelessness stuff, right? Which is some of what Cassandra is touching on, some ideas there, things around self-contained like packages, so you don't actually need to hold any state at all. You can just receive a certificate which gives you all that information, and all these kind of tricks as well. So you don't lose transaction history, at least not transaction history that's that young, right? Like you would prune transaction history that's maybe 6, 9, 10 months old. Under some conditions, still to be defined, by the way, those conditions, but you can do it. You can also do things like erasure coding within a validator set as well, which is also a nice optimization. So given a transaction, if you've got to say 100 validators in a set, then each validator only stores a portion of that transaction and you can reconstruct it later. So many options to reduce the actual load of data that any individual validator may be storing.
So, I mean, this question is obviously the answer to this question. This question and the answer to this question is concerned with the design for Xi'an, which is still some time away. The other part of this question is to do with having to trust other validators, right? So, from the point of view of
that's kind of where some of the statelessness stuff comes in.
Right.
So, if I'm given a certificate for a particular piece of state or a particular transaction that has happened in the past, but I don't have the actual transaction because it's not available anymore for some reason, right? That certificate is enough for me to be able to look at the contents, be able to determine, okay, well, what happened, right? Some payment went from there to there. I can kind of deduce some of that from the certificate. But what the certificate really tells me is these state transitions were valid, and these validators agreed that it was valid, and these validators had this much stake, vote power, whatever you want to call it, right? So even though I can't potentially see the actual transaction that triggered these state transitions, all I really need to care about is that a quorum of validators with a supermajority of vote power agreed that the execution of these state transitions was correct. So I trust but verify, I guess, which is the Bitcoin mantra, right?
And also the quorum has to have been reached. So it has to have happened within the bounds of the security of the network. So that's your trusted bounds, and that's what you implicitly trust or explicitly trust when you're using a public ledger anyway. And because Radix is a finality preferring network, that those bounds are quite high. And so if you can't trust that from other validators where the quorum is showing that you have reached the threshold required of certifications from nodes who have a certain amount of stake, then you can't actually trust the network. It's all of the same basis of
trust. Exactly. Yeah. So if I get a certificate that I can't validate, then either something's wrong with me as a replica, right? I have some corruption or whatever, or something's wrong with the validators in the network. If it doesn't objectively check out for me or it doesn't validate properly, then I have to do something else. Okay, what's happened? Is there something wrong with me? Is there something wrong with the network? And then it turns into a complicated process at that point. But your network is potentially compromised, so your only resolution is to resort to complicated practices, right? Expensive practices to figure out what the hell happened.
So it's a good question.
Yes.
Next question. Question by VandyILL. ILL on Discord. I'm designing a component token on Radix. Let's call it PiersDole. Okay, dole as in DOLE, like unemployed. Periodically, the component will need to check the price of PiersDole XRD, 2 mint new PiersDole, 3 swap some PiersDole for XRD, 4 disperse the rest of the minted PiersDole to a group of addresses, 5 pay network fees with XRD from step 3. I'm not sure if this is outside the bounds of atomic composability, as I don't know if XRD used for network fees can be contingent on the actual application, or if you need XRD in hand before starting, similar to how you need XRD to unstake.
Yeah, and this was quite an interesting question because it got me thinking. And I'll be honest, I don't know the answer to the XRD fee stuff, right? So, but it's an interesting thought in terms of, okay, I've got this complicated transaction, which like this process of events is for sure falls in the realm of atomic composability, right?
Yes.
Can deal with this, no problem. But it's more about the idea of, well, if I'm doing this transaction and at some point within that transaction, there is a net receipt of XRD that transaction owns basically until it's completed, can those XRD be used for fees? Now that does potentially get quite complicated, but
so I think the answer right now is no. However, what you can do is you can do delegated fees. So there has to be something that is going to pay the transaction at any step. And in this one, your transaction doesn't get the XRD until 3.
Yeah.
And you
With
actually
execution, basically.
you have to pay for the execution. So you can't have the execution for free. Because that then it opens up an attack vector. But what you can do is dApps, so decentralized applications and other addresses can pay on behalf of another address. So you can say, okay, you could have, let's say that in this instance, the PiersDole application developer is happy to pay for anyone who interacts with the PiersDole component. And so they have some tokens on Ledger that conditional on a bunch of things like the fact that you are minting PiersDole, it will pay for the transaction fee. If you have that and that component does have enough XRD for the transaction, then all of the things can happen, including 3, where you repay the PiersDole application for the fee that they essentially fronted you for the first 2 steps. So you can do it that way, where you still end up paying the fee for out of the swap, but there had to be someone who's covering steps 1 and 2.
Yeah.
And in that instance, you can from the user point of view, it will be that, right? They minted something, they swapped something, they got something, and they used what they got to pay for part of the fees for the rest of the steps. Absolutely, as long as you're covered for steps 1 and 2 by some other application that does have the XRD in case it fails at step 3.
Yeah, the whole delegated stuff works here, but I mean, it just got me thinking about these kind of use cases, right? And like how common would this kind of stuff be?
Yeah.
And what other solutions might there be for managing fees in this way? Right? Yeah. Obviously, I'm not talking about changing the current roadmap and giving Matt and all of the Babylon team a heart attack, but I just found it interesting that, okay, yeah, like where is the attack surface here, right? How if this became a really popular kind of transaction pipeline, and the delegated fee stuff maybe wasn't enough, or whatever, right? Reasons. Hey, we need to be able to take fees out of the middle. What would that look like? What would be the attack vectors that you would need to consider? How would you manage that and stuff? So not really any answers, I guess, other than atomic composability can do this, you could get around this problem with your delegated fee stuff. I just thought it was a really interesting kind of transaction flow, right?
Yeah, for sure. I mean, and it goes back to stuff that you and I talked about right at the start of when I joined Radix, and we were talking about having, decentralized exchanging right at the center of the protocol for exactly this kind of reason, right? So that you would always be paying your fees for transactions in some other token because of this, going back to the core of this issue of people using Ethereum have to have ETH, people using Solana have to have Sol, people using Avalanche have AVAX. And with Radix, that's not true because of delegated fees. But there is always someone paying the fee in XRD, but it doesn't necessarily have to be the end user, depending on how you want to set it up, which I think is incredibly powerful and is currently that sort of like the juncture point between.
Yeah, it's a nice midway.
Right. Exactly.
For now, for sure. I mean, it depends how frequent these kind of use cases become. I mean, if it's just once, twice now and then, I mean, yeah, who cares about just work around it.
Right. And I think there's going to be lots of applications who are very happy to pay for users using their app. Like if you're bringing in money to an app, if you're a customer, why would you not want to pay for their transaction fees? Because it lowers the barrier to entry and it makes it more intuitive for an end user to use it. And I think that delegated fee model is going to be used all of the time. It's one of the things that I think is really cool. And we spent a long time, or I say it's the royal we, because I didn't spend a long time. Matt and the team spent a long time in making sure the delegated fee model would work because we think it's going to be incredibly effective.
Yeah, I remember having conversations about kind of delegated fees way back in when we were in the first office up here in Stoke, like 2017.
Yeah.
So
where we wanted to be able to like delegated fees that become actually really complicated because it seems simple, but it's actually not simple at all. And so it really did take all of the power of the Radix engine and Scripto and our asset-oriented approach and all of these different ways in which you can do badges and permissions and all this kind of stuff to be able to get to the point where delegated fees worked in a way that was intuitive and secure. It's been on the roadmap for a long time, and it's kind of cool that it's coming out now.
Yeah, for sure. So anyway, if anybody has any other use cases similar to that, then do let me know, because it did get me thinking. So
next question is by Ranxi on Discord. How does Radix ensure that there is no downtime like Solana? And I think this actually means no downtime, unlike Solana, as in Solana has lots of downtime.
I mean, like this question was asked. This question was asked on the 2nd of May, and so it's a bit serendipitous that we're actually getting to it today when didn't have some more downtime like 2 days ago.
They recently had some more downtime. Yeah. Although it did, So
anyway, I don't want to shit on Solana too much in this question, because the truth of the matter is that building these systems is incredibly difficult. Right? There's so many moving parts, so many things you have to think about in terms of game theory, economic theory, consensus theory, and they're complicated systems. And it can be the smallest triviality that you've missed or overlooked or haven't gone deep enough in that can actually cause a real problem, right? And like Bitcoin had issues when it was first launched. Right, there was a number of kind of last minute updates and things didn't work properly, and there was forks and bugs and all this kind of stuff, right? But the advantage that Bitcoin had, of course, was that hardly anybody knew about it when this was happening, so it was fine. Whereas today, you launch a network and you've got. Well, I wouldn't say it was simple.
No, as in, in Bitcoin, the one part of the reason Solana keeps going down is there's an economic value in DDoSing the network, right? Like there's for example, max.
Yeah, I mean, take all of the subjective design decisions out of the mix, whether it's Solana or anything else. It just the pure fact that these systems are very difficult to build and difficult to test, and the problem with the main issue is that they hold value, right? So if Solana was just some consensus mechanism that was used to power a social network or a website or something, nobody would give a shit about attacking it, because it's like, well, there's no extractable value there for me.
Right.
But because these networks are cryptocurrency networks, then they just got a big fat red target on their back for hackers and exploits and all that kind of stuff. So they just get beaten to shit on a daily basis.
Right.
So what can you do, right? Well, you can spend a lot of time testing, which is kind of our approach, right? Roll it out steady, do lots and lots and lots of one more lot just to be sure, right? Test this, test that, test everything, attack it, fudge test it, everything. Because like I said, these systems are hard to
testing.
build.
That's my favorite testing.
Fudge testing, I meant, not fudge, but I mean, you can throw some fudge at it as well and see how it does. And even then, even after all that, you will have issues. And I think really we've been incredibly lucky that our mainnet has had pretty much zero issues since it went up live. I mean, I'm looking for some wood to touch, but but then we spent a lot of time testing it, and we had code audits and security audits and all this other stuff. Now, I'm not saying that these guys aren't doing that, and I'm not saying that we have a better policy in terms of our testing.
Yeah. And definitely not saying our network is perfect, because it's not.
No, of course not. I'm just saying that, whether you're a fan of Solana or Ethereum or anything else or not, just appreciate that these are complicated systems, and it's extremely difficult to get them out and for them to run without any even minor issues. So the key is just testing and keep testing, jump on things as quickly as possible. Even when your network's out there and it's running well, still do closed door testing on it, because you'll always be thinking about new ways to try and attack it and stuff. So that's the answer. And even then, chances are at some point in the future, we'll have an issue. So it's just accept it. It will happen at some point.
All right, next question. But I mean, like, let's dive to the next level of this question, actually, because I think it's a good question. So, like,
okay,
there are some things that are inherent in how Solana has been designed, and actually, this would be a good question for me to ask on the round table, because this is more of a Russell Matt question, but it's to do with being able to DDoS leaders, and how the network protocol has been designed. I've actually
highlighted another question on the sheet that talks about that.
Okay.
So, because it's very relevant.
Oh, okay. Yeah, here we go. Right.
Yeah.
Next question. Let's go on to the next question then. Okay. So, question by Sergis Forake on Telegram. Hi there. I would be grateful if someone from Radix could answer me. I have several questions regarding the Radix consensus protocol, specifically the election of a deterministic and predictable leader. There we go. This means that there are attack vectors such as the adaptive attack on leaders. On the white paper March 2020, it does not specifically specify which solution they adapt to this problem. Is there any update on this?
Okay, yeah. So at the moment, for us and many of the networks out there, they use quite a simple leader selection if you're using kind of leader-based BFT stuff. So like hot stuff, PBFT, Tendermint, all those kind of things, right? And there's some variation in terms of how the next leader is selected or how that's determined. But they're all quite weak in terms of their DDoS like resistance, right? So one of the things that I've been looking at alongside stuff with Cassandra and other stuff I'm working at with all my many spinning plates is actually how do you have a provably random yet still deterministic mechanism of selecting your next leader, right? And so like really there's two options. There's two kind of defenses against DDoS when you have leader-based consensus mechanism. One is you have a lot more leaders, right? So the more leaders you have, then the more that have got to be DDoSed to cause liveness issues in the network, right? So, if I've got 100 leaders, then I need to take out 34 of them and potentially, of course, a liveness issue. If I've got 1,000 leaders, then I need to take out 350 to cause a liveness issue, right? So, and that's more difficult to do in terms of resources, right? I mean, you can use amplification attacks and stuff, but still, right? More is better, yeah? And the second one, obviously, is to ensure that the next leader, the next entity that's going to be the leader, the next actor is unknown. Because at the moment, if you know it, well, you don't need to attack 350. You just need to attack one if you know who it is, right? You can send all your resources at them. So by making it random, you're kind of forcing your attacker to have to go with the former. You've got to attack pretty much everybody because you don't know who it's going to be, right? Or you've got to attack to a third of the network so that consensus can't be arrived at. And so this Cassandra kind of delves a little bit into more leaders, more potential leaders, right? So you've got a larger set of validators that are doing consensus on a particular thing. And even though Cassandra is leaderless, a lot of the things I've been looking at within Cassandra are relevant to leader or leaderless based networks, right? In terms of efficiency and how you're packing certificates and stuff like that, reducing communication complexity, authentication complexity, all that kind of stuff. So regardless of what underlying mechanism, there's a lot of primitives in Cassandra that would be helpful there. So you can increase the number of potential leaders that you have. And the other thing I'm looking at is doing some of this with UCD as well, Professor Mo. Is how do you randomize the selection of your leaders in a way that is deterministic, i.e. it can be verified after the fact, but you're not able to guess who the next leader is going to be until you've arrived at some kind of threshold of kind of like a passive consensus or something that tells you who the next leader is, right? And it will also make it very hard to influence and stuff like that. And so they're the two kind of different tracks that I'm working on behind the scenes to kind of mitigate these kind of problems. And for sure, some of that will have to make its way into later network releases, because at the moment, if we were over the next 12 months to have total value locked in our network that would approach levels like Solana, then we would probably start to see some of the same kind of attacks.
Similar, like the thing is that the network architecture is actually quite different for Radix than for Solana.
It is different. It is
so
different.
I've had this conversation with Matt several times, and I feel like this is another good one for the roundtable again for Matt and Ross. But there are a number of reasons why DDoSing leaders on Radix is harder anyway, even before we get to sort of Xi'an, than it is with things like Solana. Though I'm not sure on the details, so that's something that we can.
No, yeah, I wouldn't call them directly compatible, directly the same, right? But if you've got a predictable leader selection, then you can bet your bottom dollar that someone at some point is going to put the effort in to find a way to take one or more of them out. So.
Yeah. Cool. All right. So next question is decibels on Telegram. I was listening to Twitter Spaces with Dan explaining why the validators prune off some of the shards they validate on when the network grows to be able to keep up with the increase in load. This way. Not all validators have to validate every transaction which is unavailable. This made me wonder how many validators are there for a particular transaction. I know it is 2f plus 1, but what is the number of f? What is the number for f? The number of allowed faulty nodes? Is it a fixed number or can it vary? And if it's fixed, what number is it?
Oh yeah, good question. So yeah, we know why validators prune off, right? So as the load increases, they serve an ever decreasing number of actual shards within that group, so that the amount of data they have to store, etc., is less, right? So that gives you your linear or close to linear scalability, depending on what the load looks like at that time, right? F in consensus theory does indeed refer to the number of faulty replicas that you may have, right? Now, those replicas may actually be faulty they may have disappeared for some reason, internet connection problems, or they may be malicious, right? You just don't know. You can never find out. So in terms of a supermajority, the reason it's 2f plus 1 is that if your non-faulty actors have come to some agreement, then to ensure that the faulty actors can't subvert that agreement later, then your agreement needs to be 2 times f plus 1 more, right, to break any kind of deadlocking, basically. Yeah. So if there's 100 validators in the network, then you can at most tolerate 33 of those validators being faulty in some degree, right? And to come to consensus, you need 2f plus 1, which in this case is 67, in order to be able to form an agreement, a quorum, a certificate, right? And if you think about the way that maths works, then it makes sense, because there's no way that the 33 can fool the 67 into disagreeing with each other or changing their opinion or whatever, right? There just aren't enough numbers in the 33 to be able to then subvert what the 67 have come to agreement upon. Now, what's interesting with F is that F changes, right? So F is more like saying there is a ratio of faultiness that this network can tolerate, right? So F is 33%, basically. So however many validators you've got, in our case, for our consensus mechanism, F is a third. And some other consensus mechanisms, depending on what they're doing, it can be less, right? So in some consensus mechanisms, F is 20. Depends on a bunch of things, like how many consensus phases you've got, and if you're synchronous, semi-asynchronous, et cetera, right? So there's a lot of factors that play into it. And there's actually some good research that digs into some of that, actually, which I know there's going on at the moment elsewhere. So the F is varying, right? But if you think in a proof of stake network, well, your different validators may have different amounts of influence, right? So in a proof of stake network, what F actually refers to is the amount of stake that is faulty. So if there's 100 million stake that's in the network, then at most 33 million of that stake can be controlled by faulty actors. So in the case of proof of stake, F actually refers to stake, not the quantity of validators. So in the case where you had 3 validators, and one of them had 40 million and the other 2 had 30 million, then you potentially have an issue if the one that controls 40 million is faulty, right? Even though you've got 3 validators. And it gets a little bit complicated there in terms of reliability of actors and stuff like that. But essentially, F represents vote power, basically, in terms of what your validator set, how much vote power they control. So in a simple, each validator has 1 vote, then F maps to the number of validators. In something like a proof of stake, F maps to the stake.
Cool. So I think this is going to have to be it for today. We do have a bunch more to get through, but we're going to have to come back to them. We
started late because somebody, didn't we, Piers?
Yes, that was my fault. I may have been on the wrong link, and I was like, "Where's Dan? What's he doing?" And he was.
And I'm sitting here thinking, "Where's Piers? It's a really long shower."
It was a really long shower.
Yeah. While asleep.
Had a little nap in between. It was
that's it. Why not? A little nap between meetings.
Do you not nap between meetings? Is that not your thing?
Oh, hell no, man. I don't nap well at the best of times, let alone between meetings. I just end up thinking about what I've got to do in the next meeting.
So, yeah, we will be back in a month, and we will have a special episode for you in a month, won't we, Dan?
Yes, we will. Yes, we will dig into the whole dank sharding stuff, because that's quite interesting. And the way that a lot of the ideas and stuff in there overlaps with a lot of the ideas that we've had. But there's also some differences, and like what I think's good, what I think's bad, what I think is forced design traces because they've got to build on an existing thing and stuff. But yeah, it's very cool. If you haven't got into the dank sharding stuff, it's a rabbit hole. So
So this is Ethereum V2's roadmap that they're now rolling out, and they're starting with proto dank sharding, and then moving to full dank sharding, and we will have a dive into the world of dank sharding, because I'm sure that we'll be asked many times. So we thought we would do a special episode.
Get ahead of it. Yeah. Sounds good. But yeah, there's quite a lot of meat in there, so I need quite a lot of prep time because I wouldn't want to get anything wrong and sound like an idiot.
And whereas I am perfectly happy to get things wrong and sound like an idiot.
You can just point to somebody else and say, oh, I got it wrong, ask him. Whereas I can't do that.
All right, thank you very much, Dan. And
okay, no worries.
See you soon.
Bye-bye.